Okay, so Thevenin's theorem, as stated, states that any two-terminal network containing resistances and voltage and current sources may be replaced by a single voltage source in series with a single resistor. In effect, what Thevenin is saying, if I have a network, doesn't really matter what's in there. Right, so this is my network. Right? It has resistances, it has sources, that's voltage, current sources. Yeah. That two-terminal network, if I look into those terminals, then all of this network can be replaced using a simple circuit, which looks like this. All right? They're saying that that network can be reduced to a single voltage source, which will, of course, have a voltage E Thevenin in series with a resistance, which we're going to call R Thevenin. All right? That's what the theorem really is saying. Our task, therefore, is to define that E Thevenin and the R Thevenin. Right? What's E Thevenin and R Thevenin? And the EMF of that voltage source, this voltage source that we're showing here, the EMF of the voltage source is the open circuit EMF at the network terminal. So at these terminals, I call them AB. Thevenin is saying if I can find the voltage at those open circuit terminals, then I'll be able to find the EMF of the source. And then he goes further to say that the resistance would be the resistance looking into those terminals. So again, if I look into these terminals, yes, I can find R Thevenin, but I will look into those terminals under one condition, and that is the sources that are in the network are replaced by their internal impedances. So if we have a current source with an internal impedance of infinity, replace it with an open circuit. If I have a voltage source, which has an impedance of 0, I replace it with a short circuit. All right? So that is the sum total of the theorem. Our next step, therefore, is how do we apply this theorem in terms of circuit analysis? And to do that, we're going to focus on the question that we have been looking at since we started network theorems, all right? So here's the question. And we want to find the current flowing through the 24 ohm resistor. So in the space in your notes, just put the circuit for me and the question. Okay, so we want to find the current through the 24 ohm resistor. And by virtue of Thevenin's theorem, we're finding the open circuit voltage and also the resistance looking into those same pair of terminals with the sources replaced. Okay, so our first step is to simply remove the resistor. So we redraw our circuit and we remove the resistor for which we have interest. So that 24 ohm resistor, we remove it. And given that you're being introduced to the theorem, I encourage you to redraw the circuit with the resistor removed. And based on the circuit that we're seeing here, the voltage across these open circuited terminals, obviously there is no resistance anywhere here. So there wouldn't be a voltage drop. So the point here, AB, on my, where I have removed the resistor, would be the same as XR. So in other words, E Thevenin, based on what we're seeing here, would be equal to the voltage XR. So the open circuit voltage would be the voltage across this entire branch. Now, it is totally up to you. It is totally up to you. I will make the points here. It's totally up to you as to the method you use to calculate the voltage. All right. So we have gone through all the theorems: superposition, mesh, nodal. This is where you start putting it to use. So you determine which one of those methods you consider to be most appropriate. All right. Whichever you find easiest. And as we said earlier, the open circuit voltage will be the voltage across the combination of the 6 ohm resistor and the 35 volt source. Okay? Now, because of what we're trying to find, yes, it would be best, the easiest method or the most appropriate method, maybe the node voltage method. Now, I'm not telling you that because we are finding the node voltage that, or the open circuit voltage, that we must use nodal. That's not what I'm suggesting. We can use mesh, right? We can use superposition, but in this instance, it may be most appropriate that we use nodal. We get to the answer, straight off the bat. So in doing that, I identify our nodes. Now, students, last week when we looked at nodal analysis, one of the things I said is that the principal nodes that you consider would be those where you had current division. All right? So in this instance, you would have considered just one node. For this network, you just have one node that you would consider as principal node. And that would be fine. It will be fine. It just means that you would have to do an extra step. And I'll show you that using the next example. But in this instance, there is nothing wrong in making this point a principal node. And if you do that, then all we're looking at are the currents leaving that node. So we have the current through the 8 ohm, we have the current through the 6 ohm. Through the 6 ohm, it is V1 minus 35 over 6. Through the 8 ohm, it's V1 minus V2 over 8. And we simplify that, and that's our expression.
Sir, one second, my camera. That'll work.
For node 2, we'll be looking at the currents leaving node 2. So from node 2, the current through the 8 ohm resistor would now be V2 minus V1 over 8. Current through the 5 ohm would be V2 plus 25 over 5. And for the 20, to be V2 over 20, which is what we have here. All right. Now at this stage, I'm not going to, well, I haven't been asking or showing working, but I expect that you will work them out on your own. All right. So if we solve for V1, then V1 is equal to 16.667 volts. Now note, there is no real need for us to find V2 because what we are interested in is Thevenin. And Thevenin was the node voltage V1 because V1 represents the voltage between that point and the reference. Good? Which would be the voltage across the 6 ohm and the 35 ohm resistor. Are you clear with that? All right, so there's no need to find V2. So V1, which is equal to Thevenin. So we go back to the notes, and so that was just step 1, where we find the open circuit voltage. All right. Step 2 in the process is that we now need to find the Thevenin resistance. And the Thevenin resistance, as defined, we defined it earlier, yes, is a voltage seen looking into those terminals when the sources were replaced by their internal impedances. We have two voltage sources, so we replace them using short circuits. All right, so we redraw our circuit, and we are finding the resistance in looking in. Now, by now, again, I expect that you are now comfortable with writing these resistance equations. So you're looking into these terminals for the resistance. So redraw your circuit, please, and go ahead and calculate our Thevenin for me. The resistance are Thevenin. Based on the circuit, the equation, 6 in parallel with 8, which is in series with 5 and 20 in parallel. And that gives us 4 ohms. All right, so the equivalent circuit would be the voltage of 16.667 in series with your 4 ohm resistor. So this is a Thevenin equivalent circuit. But remember, the objective was to find the current through the 24 ohm resistor. All right. So to do that, we now need to connect the 24 ohm resistor to the Thevenin equivalent circuit. All right. So we connect that. So this is my Thevenin equivalent, yes? And I'm reconnecting the load to it, which is a 24 ohm resistor. And the current through the 24 is therefore 595.24, which is 16.667 over 28. All right. And as you will agree with me, this was the same current value that we determined using the other methods that we have been introduced to, whether it was nodal or mesh or superposition, because we analyze the same circuit using all 3 methods. All right. Do you have any questions before I move on?
Sir, you can go back 2 slides for a second, please.
Tell me what you want, Mr. Nelson.
Step 3. I didn't finish writing off step 3.
Step 3 is in your notes. There's nothing for me to go back to. That's what I said at the beginning, that the steps are all in your notes. All right. Okay, so let's take another example. Again, this is another circuit that we looked at using nodal. And the question here is for us to find the current through the 8 ohm resistor using Thevenin's theorem. So go ahead, take the question, and then we'll go through it. Okay, so what's the first step?
Remove the resistor of interest.
Speak up, Mr. Jackson. Can't hear you clearly.
Remove the resistor of interest, sir. Remove the 8 ohm resistor.
Okay. So if we do that, all right, so we're going to be finding Thevenin at that point. The resistors, we have 2 ohms, we have 2 amperes, 5 ohms, 13 ohms, 3 amperes. Okay, so that's our circuit. Now, based on this circuit, with the opening at the 8 ohms, which method would you want to use to solve this?
Nodal
Everybody.
analysis.
What's that, Mr. Reed?
Nodal.
Okay. All right. So in using nodal, which guide me. Tell me what you wanted. We're trying to find Thevenin. So, where would I be trying to determine the node voltages?
All right, so I'll put V1 between the 5 ohm and the 2 ohm, and V2
Okay.
between the 5 ohm and the 4 ohm.
Okay. Where's my reference? Where do I want to put the reference?
Oh, below the circuit.
Okay. Just for the record, students. If I give you a question and you say that you're using nodal, or if I direct you to use nodal, and there are no, and you do not identify the nodes, irrespective of how perfect the equation that you form may look, if the nodes are not clearly identified on the circuit, yes, then you will not get a mark for anything. All right, it's automatically 0. In the same way, if you're doing mesh analysis or Kirchhoff's laws, and you have not properly indicated what you are doing on the circuit, yes, it's automatically 0, regardless of the answer that you provide. So I just want to put that out there. Everybody keep that in mind. All right, so Mr. Reed, I'm going to stick with you. All right. Let's
Yes,
have
sir.
the equation. So at node 1.
So at node 1, 0 is equal to -2 amps.
That's it.
No, sir. V1 minus V2 over 5.
I'm assuming
Yes, sir.
this is what you're saying, right?
Yes, sir. Yes, sir.
All right, so we simplify this, so we get V1 minus V2 is equal to 10. That's your first equation, yes? All right, let's go to node 2 now.
All right, so for node 2, V2 over 7 plus 3 amp equal to 0.
How many branches we have connected to node 2? Sorry?
3. Oh, 3. V2 minus V1 over 5. Yes, sir. Plus 3 amp.
All right, so that quick check. That quick check in terms of the number of branches connected will help you to avoid errors. So the
Yes,
same
sir.
way you were leaving out one branch, yes, just look quickly. You see 3 branches, it means that your equation must have 3 components. Fair enough? All right, so thank you very much, Mr. Reed. We can simplify this. We multiply through by 35. So we get 5v2 plus 7v2 minus 7v1 is equal to minus 105. Or minus 7v1 plus 12v2 equal to minus 105. And we solve this for v1. V1 is equal to that's v1.
Negative 45.
That wouldn't be correct.
3, sir.
That's how Mr. Vasa?
3.
3. All right, so V1 is equal to 3 volts. Now, earlier I said to you that it is up to you as to whether or not you use the 2 nodes. So, based on this 3-mesh circuit, I'm just going to use 1 node. And note I am calling it VA. All right? So you'll have a current going in this direction. You'll have a current going in this direction. You have a current going in that direction. All right? So since I had very good feedback from Mr. Reed, I'm going back to him, so I can count on him now. Mr. Reed, so we have 3 currents leaving VA, leaving node A. All right? No, man, don't get worried. Come, relax your brow. Relax your brow. Relax your brow. All right? You don't have to make up your brow. Don't be scared. You ready now?
Ready, sir.
Good. So we have 3 branches attached to node A. What's the current in this branch?
3 amp.
Good. So we have 3. What's the current in this branch?
V2 minus.
No, Mr.
No,
Mr. Reed,
no.
note. There's no more V2 and V1. It is 1 node that we're looking at, and it's VA. So let me take off the V1 and 2. It's VA. So what's the current in this branch? It's not a trick question. Let's look at it. What's the current?
PA over 5.
No.
No.
Look at the branch. A current that is going in this direction, where would it go? It will go through the 5 ohm resistor. Agreed?
Yes, sir. Yes,
Where
sir.
it go from? Where it go beyond that?
To the 2 ohm.
And where?
To ground.
All right, so look at it now. What is that current?
2 amp.
Exactly. You see, you keep it simple. All right. Now, is it 2 or is it?
-2.
Thank you very much. You see, as soon as you start relaxing, the bro will just come now. All right. And what is the current in this direction? From A.
One.
No, we don't have 1 there. Remember, this is VA, you know. What's the current in this branch?
VA over 7.
Exactly. So plus VA over 7, and that's equal to 0. Yes? We good now?
Yes, sir.
So we have, therefore, that VA over 7 is equal to -1. Our VA is equal to? That's if VA over 7 equal -1, that's VA.
-7.
-7. So you see, in one line, yeah, you finish the question. All right? But remember, what we want is the voltage across these two. Yes? And what we have is VA. So I now need to determine the voltage drop across the 5 ohm. All right, so Mr. Reed has done quite a bit, and I thank you, Mr. Reed. We're now going to give
Yes,
somebody else another chance. What would be the voltage drop across the 5 ohm resistor?
And sir,
Pardon me? What's the voltage drop across the 5 ohm resistor?
10 volts.
10. Now, give me the polarities, Mr. Burkett. Which side will be positive, which side will be negative?
The positive would be to the left side. All
right.
Resistor.
So it will be plus, minus, and that's 10 volts, okay? Burkett?
Yes, sir. Yes, sir.
Yeah, so if that is 10, and I now want to find Vx, what would Vx be equal to? Remember now, VA is -7. So what is Vx? Burkett?
So you'd subtract the.
No, don't tell me what you do. I just want to find Vx. What is Vx? All right, anybody else? What is Vx?
3 volts.
3 volts.
3 volts. And Mr. Bailey,
Yes, sir.
give me the theory now regarding how you get the 3.
All right, so VA minus, you're going a voltage rise, so it'd be a +10, and go to the Vx, so that would give you 3 volts.
Absolutely. So you have VA to be equal to -7, and you have a voltage rise of 10. So it is -7 plus 10, and that gives us 3 volts, which is the same thing we got earlier. All right? So in terms of the nodal analysis, yes, which is what we did here, all right, it's one line. And you get your solution in no time. Fair enough? However, you'll have to do some additional work in order to get the voltage across the open circuit, which is your Thevenin. So whichever method, and there's no easy way to do this. You're just going to have to practice. All right? You just have to put in the work, just have to practice. You're not going to see this, it's not going to be jumping out at you. All right, this comes with experience. So now that we have the Thevenin voltage, so E Thevenin is 3 volts. We now go to step 2, and step 2 requires us to replace all the sources with their internal impedances. What is happening here? Just give me a minute. Let's get back there. All right, so we now replace the sources with their internal impedances. We have current sources, so we put in open circuits. So what's the impedance? What's the resistance seeing looking inside?
12 ohm.
So our Thevenin would be 5 plus 4 plus 3 to give us 12 ohms. Thank you. So my Thevenin equivalent circuit would be a 3 volt in series with 12 ohms. The resistor that we are interested in is an 8 ohm resistor. So I'll simply connect that 8 ohm. Which means that the current through the 8 ohm will be 3 over 12 plus 8, which gives us 150 milliamperes, which of course is the same value that we got when we did it using the other methods. Any questions? All right, so we push on. We want to run now to Norton's theorem. And Norton's theorem is we call it most of what we will speak to with Norton's theorem is the antithesis of Thevenin. So again, it describes a two-port network or two-terminal network. Same network having resistors and voltage and current sources. And it says that it can be replaced by a single current source in parallel with a single resistance. So the same network that I spoke to at the beginning, that's what is being reflected here again. So in this instance, however, whereas Thevenin said that we had a voltage source in series with a resistance, Norton speaks to a current source in parallel with a resistance, which is why I said that you know, they are opposite, so to speak. So one speaks of current, one speaks of voltage, one speaks of series, one speaks of parallel. Yep. Now, in defining the current, the opposites continue. All right. In defining the current, the opposites continue. So for the Norton current is the short circuit current. For Thevenin, it was the open circuit voltage. All right. So in Norton, it's a short circuit current. And Mr. Jackson, you still with us? Philip?
Yes, sir. Yes, sir. I'm still here, sir.
I can't see you, man. I can't see you. I'm assuming you're not here, you know. Same thing goes for Thompson.
Laptop screen. That's it.
Okay, that's better. Okay, so with no response from Thompson, we just make some adjustments. All right. Okay. All right. So again, with Norton, we're dealing with short circuit current. Thevenin, open circuit voltage. And again, if you look at the definition for the resistance, you'll see that it is similar for both. So the resistance is the resistance in looking into the terminals when we have replaced the sources by their internal impedances. All right. So it means, therefore, that R Thevenin is equal to R Norton. So they are one and the same. So we go back to the circuit that we started with. So it's the same question. All right. So I'm going directly to the steps because you already have the question. All right. So the first step, whereas we open circuited the path with the 24 ohm resistor, in this instance, we're going to short circuit the terminals because we're finding I Norton, and I Norton is the short circuit current. So we have the 24 ohm resistor, we replace it with a short circuit. All right, so go ahead, redraw with the short circuit. Okay, so now that I have this in place, the question is, and again, you know, we have established that the method you use is totally up to you. But for obvious reasons, we want to find the current through this section of the circuit. It would suit us just to use Norton. What did I say? It would suit us to use mesh analysis, right? So it's your choice. Totally up to you. This is the one time you get some freedom of choice in network. All right. But of course, you need to exercise that freedom with some care. So in using mesh analysis, this is what our circuit will now look like. So we just put in the mesh currents. And obviously, I1 would be equal to I Norton. So we just go ahead. Write our mesh currents, our mesh equations, and solve simultaneously. At this stage, I don't think I need to go through with you step by step in terms of the mesh currents or the mesh equations. So I'll just give you the equations, okay? So you have the three equations, right, for mesh 1, 2, and 3. So those are the equations. And if you solve them simultaneously, then that's the current. Okay. We have this. All right, so now that we have the Norton current, as I said before, the resistances will be the same. But for completeness, I redraw my network and I find R Norton. And as you can see, it will be the same as with the R Thevenin, which is 4 ohms. All right, so it's the resistance seen looking into these terminals. So the Thevenin equivalent, what's wrong with me today? The Norton equivalent circuit will be as shown. So that's your Norton equivalent. You have a Norton current. And note, since you're going to use calculators, I suppose you get all 3 values at the same time. But back in the day when we had to work them out longhand, based on the original circuit in terms of the mesh analysis, all you would need to calculate would be I1, because I1 is the current that corresponds to the Norton current. All right, so if you were to do it longhand, then there's no need to calculate I2 or 3. All right, so you would make the appropriate substitutions. But as I said, that's when you would be doing it longhand, which is not the case today. All right. And remember, our objective was to find the current through the 24 ohm resistor. So I would now put that back in the circuit. So I've put the 24 ohms resistor back in the circuit and found the current flowing through it. We have 2 resistances, so we can apply the current divider. And if you do that, you get a current of 595.24, again proving the theory. Once again, I pause to ask, do you have any questions with what has been done? Have I lost you? Or how long ago have I lost you? All right, no questions, we move on. So we have looked at the Thevenin, we have just looked at the Norton. Yes? The Thevenin, we had the 16.667 in series with the 4 ohm. And for the Norton, we have the 4.1667 in parallel with the 4 ohm. Now, it wouldn't necessarily be obvious. However, I'm now highlighting the fact that the Norton current is equal to the Thevenin voltage divided by the Thevenin resistance or the Norton resistance. So the relationship between Thevenin and Norton is that the Norton current is equal to the Thevenin voltage over the Norton resistance. What this is telling us, students, is that, I mean, the two networks that we have looked at, they are relatively simple networks to analyze. But I guarantee you that you're going to come up against, much more complex networks, which you will need to, reduce to Norton or Thevenin. So being able to determine one, even if it's the other that you need, may be helpful, because you'll have a circuit that it is much more difficult to find a Norton current than the Thevenin voltage, or much more difficult to find the Thevenin voltage as against the Norton current. But of course, I know that, so I would, ask you for the more difficult one. And you would then have to make a determination in terms of finding the other equivalent circuit and just make the conversion. And then using the term conversion, that is something that you would have been doing if you did any electrical in high school. You would have gone through what they call source conversion, converting from a voltage source to a current source. Yeah. So it's not really source conversion, it's really looking at the Norton and the Thevenin equivalent circuits. Okay? But the most important use, I would say, is that because there is a relationship between the two, there are certain circuit configurations that will require you to use both. Because our Norton, our Thevenin, is equal to E Thevenin over I Norton. Now, the statement you have in your notes regarding Thevenin's theorem, where it says for the Thevenin or Norton resistance, it says it's the resistance seen looking into the pair of terminals when the sources are replaced by their internal impedances. All right, that's how it describes the Thevenin resistance. However, by definition, you know the internal impedance of an independent current source. You also know the internal impedance of an independent voltage source. However, when it comes to these fellows, the dependent sources, you have absolutely no clue what the internal impedance are equal to. And it is for that reason that once a dependent source is included in the circuit, you are mandated to find I Norton and E Thevenin in order to find R Norton. So before we get into that, here are the points I just made. So the relationship between Norton and Thevenin, we call it source conversion, but it's not really source conversion per se. It is the Norton and Thevenin equivalent circuits. All right? Secondly, it allows you to determine one and convert to the other. So if I want the Thevenin equivalent, but for you, it is easier to find the Norton, go ahead, find the Norton, and then convert it to the Thevenin. All right? But the most important link between the two is that in finding the Norton resistance or Thevenin resistance, yes, we have to replace the sources by their internal impedances. However, when you have dependent sources included, it's impossible because you do not know the internal impedance of the dependent source. Unless, of course, you're given it, but you know, we just take it that we don't. So these are the 3 points. You can note them and then we. Okay, so moving right along. Here we have a circuit that has both an independent voltage source and a dependent current source. All right? So we have our independent voltage source, and here's our dependent current source. Once you have that combination, it means that you must find your I Norton and your E Thevenin. All right? Because that's the only way you're going to find R Norton or R Thevenin. All right? So let's go. Now, note all I have put here is the a variable load. Okay? It doesn't matter what that resistance is. Once you have the Thevenin or Norton equivalent, you can put in any resistor there, and you'll be able to find the current through it. All right? So we're just putting that resistor in place. Now, as I've been saying to you since we started this afternoon, the method you use is totally dependent on you. You decide what method you are going to use. All right? But since I am now in charge, I'm going to use the method I want. All right? So I'm going to use nodal. Okay? And I'm also going to do something that for you may seem a little unorthodox. I'm also going to put my reference at this node. So that's my reference node. Which means that what you would normally have at the bottom traditionally as the reference, I am now calling that node 2. And I'm making this my node 1. So those are my 2 nodes. So I have my node 1 at the top. I have my node 2 at the bottom. Just out of curiosity, if I had done it the traditional way, meaning have nodes 1 and 2 at the top, how would that affect your calculations? And just looking at what I now have on screen, how would it make how is this making the analysis easier? Anybody? If I had nodes 1 and 2 at the top, how would that impact? What's that, Ms. Alexander?
I'm saying, sir, you would have a super node if you had put node 1 and 2 at the top.
Exactly. Because I would now have a source between two principal nodes. So the fact that I put the reference up top, right, it gives me a simple solution for node 1. So what would node 1, what would V1 be equal to?
Minus 12 volts.
Why is it minus 12, Mr. Hawkins?
Because leaving V1, there would be a voltage drop if it's entered.
Okay, so let us do it. Let's use the approach you are using. So we have V1. If I have a voltage drop, what next do I write?
Not understanding the question, sir.
If I'm starting at node 1, so I have V1. We are going from right to left.
Yeah.
Good. So it's a voltage drop, as you just said.
Yes, sir.
So
Well,
what do I write?
So V1 over 6.
We're talking about V. We're looking
Oh,
at
right to left.
this.
Sorry. Yeah. Minus 12.
So V1 minus 12. And where we end up?
Yeah. Oh, 0.
What is V1?
V1 is 12. Yeah.
People, go back to the basics. Do not try to jump over this thing. I tell students, shortcut draw marks. Right? I know I'm from the country, so we used to say shortcut draw blood. Right? Shortcutting networks, draw marks. Stick to the basics until you are fully comfortable. So V1 is not minus 12, V1 is 12. Well, let us look at node 2. So we have dealt with node 1, V1 equal 12. That's your first equation. Now let's look at node 2. How many branches are connected to node 2? And you know, I'm going back to Mr. Reed because we discussed this already, right? So I'm coming back to you. How many branches do we have connected to node 2?
3.
3, sir.
No, don't repeat what you hear. Look at
4,
it.
sir. 4. 4, sir. 4.
Don't want you repeat just because it's
Whenever I hear him, sir. Whenever I hear him, sir.
All right, man. I repeat it. If me say I repeat,
No.
I repeat. All right, sir. So let's go again. So it's 4 branches. Good. So how many components should the equation have?
4.
4. Good. So we have 1, 2, 3, 4. All right. So for let's call it, that's 1, 2, 3, 4. All right. So for branch 1, we are at node 2. For branch 1, Mr. Reed, what is the current there?
Branch 1. V2 minus V1 over 6.
V2 minus V1 over 6K. Good. Branch 2.
V2 minus V1 over 3K.
Branch 3.
V2 over 4K.
Branch 4.
Minus 2Vx over 1000.
No, Mr. Reed.
Equals 0.
Not because me a trick you, but tell me the truth.
No.
Tell me the truth.
Yeah.
When you look at it using the basics, you don't realize it's simple.
Yes, sir.
So you start first by looking at the number of branches. And you just pick off each of the branch then. And that's the equation. So Mr. Reed has declared it that it's easy. Huh? You know, you can't get it wrong again, right? I'm just saying. So the equation at node 2 is as shown. If you go back to the original circuit, the initial circuit, Vx is the voltage across the 3K, right, with the positive at the top. So it means that Vx is equal to V1 minus V2. And so you can make that substitution. All right? So even though we're dealing with node 2, because Vx is given, let me go back so everybody know what I'm talking about. That's Vx. And we have this as node 1 and this as node 2. All right? So again, use the basics, V1 minus Vx equal V2, which means that V1 minus V2 equal Vx. I'm putting the voltage as a fraction, but it's totally up to you. Use your decimals. That's what you're comfortable with. It doesn't really matter to me. All right? So we have 120 over 11 V. But remember, what was the objective? The objective was to find the current through the short circuit. Okay? So we have V2, we have V1. So the current through the short circuit would be V1 minus V2 over 6K. We get 2 over 11 milliamperes. We now need to find the open circuit voltage. So I'm going to open circuit that path. All right? And I open circuit the path, or the port. Yeah. So between AB, I have the open circuit. All right? So with that open circuit, no students. And this is why I say stick to the fundamentals, stick to the simple things. A while ago, when I went through it with Mr. Reed, all right, and we identified the 4 paths. Yes? With the open circuit, you realize that we have opened one of the paths. Fair enough? So if you look back at the equation, and that's part of the reason why I use nodal analysis, I would have removed this path. The V2 minus 1 over 6. I would have removed that path. So the equation, I already have it. I've just removed that path and recalculated. So V1 is still 12. V1 is still 12 volts. But for the V2 equation, this is what we now have. Because I now have 3 paths. The path through the 3K, the 4K, and of course the current source. And of the voltage across the 3K would be equal to the open circuit voltage because no current will be passing through the 6K. I6K would be equal to 0. So there's no voltage drop. So whatever the voltage is across the 3K would be equal to the voltage across the open circuit. And this is something that you need to have clear in your mind, that you can have a voltage present without a current flowing. So you don't need a closed path for a voltage. You need a closed path for a current. But if voltage is a difference in potential between 2 points, that don't require a closed path. All right? As a matter of fact, completely the opposite, because if you want to make the voltage 0, then you would close the path or short circuit, create a short circuit. Anyway, that's for another time. Okay. So now we have V2. Remember what we are seeking to find is the voltage across here. So we have V2. Yes. We have V1, which is 12. So V open circuit would be V2 minus V1, or V1 minus V2, whichever. Okay. So the open circuit voltage is V2 minus V1, which gives us 36/31. And our Thevenin is the open circuit over the short circuit. Open circuit voltage over the short circuit current. And that gives us all right, any questions? Now that I have the Thevenin resistance, of course, you know that the open circuit voltage is the Thevenin voltage. So this is equal to E Thevenin. And the short circuit current, yes, is I Norton. All right. It means I now have both the Norton and the Thevenin equivalent circuits. Okay. So we have looked at first circuit. We had, we had voltage sources only. The second circuit, we had current sources only. But in both, we had independent sources. That's the key. We just looked at a network with both independent and dependent sources. However, we can have one which only has dependent sources. Now, by definition, a dependent source, the output of which depends on the current or voltage somewhere else in the circuit. All right? How that is connected is not of importance here. What we know is that the output of that dependent source is dependent on the voltage or current elsewhere. But that current or voltage that is produced must be coming from some other source. So if you have only dependent sources, then as we have stated here, the circuit can't self-start. All right? So the open circuit voltage and short circuit current would be equal to 0, which is impossible. Yeah? Well, I shouldn't say impossible, which is expected. It's expected. Okay, you have no internal source. However, we can calculate the Thevenin resistance. All right? Which is the same thing as the Norton resistance. Yeah? And all we're doing here, students, is to, by use of a better word, measure the resistance of the circuit with the dependent source being present. And that is done by applying the principle, the same principle on which the ohm meter works. What is that principle I'm talking about? If you have a voltage source and you connect it to a circuit and find the corresponding current that flows into the circuit, then that gives you an indication of what the resistance is of the circuit. Or if you have a current source and you apply that to the circuit and find the corresponding voltage, then again, you can find the resistance. So that's the principle we're going to apply. So let's go. So to determine the resistance, an independent voltage or current source is connected at the terminals, which is what I just said. So you're either going to connect an independent current or an independent voltage. And you dictate what that voltage supply is. We try to use nice, clean numbers, 1, 10, 100, that sort of thing. Easy to divide, easy to multiply, easy to work with, right? So you decide the magnitude of the source. And then you're going to find the corresponding current or voltage. So note the difference or the combinations. You're going to attach a voltage or current and then find current or voltage. So if you attach a voltage source, you find the current. If you attach a current source, you find the voltage. All right? So in terms of application, here's a circuit. Take that from a place. Let's go through this. All right, so with this circuit, what we're going to do is to attach a voltage source. So we're going to insert a voltage source. So as I said, you dictate what the magnitude of that source is. This instance, we make it 1 volt. There are 1 volt source attached. And the objective is that we then find the current that is flowing from that source. We're going to use nodal analysis, all right? Obviously, once we have found V1 and V2, then we'll find the currents. that are within the circuit, and from that we can find the current that is flowing from this 1 volt source. Again, there's no point in us trying to find, let's call that VA, because VA would be equal to 2Vx. All right? So we can leave that one out. We know it's equal to 2Vx, the potential at that point. I mean, VA is 2Vx, so, all right? So let's write the nodal equation. All right, I'm not going to ask Mr. Reed again. Anybody else want to make an attempt? Let's start with node 1. I'm sorry, nobody wants to put themselves out on the line. So since you and I have it, Pat, we're just going to give them the equation. All right? So we have V1 over 1K plus equals 0. Vx is equal to V2 minus V1. Right? And in terms of, we have 2V1 plus minus plus minus. So V1 is equal to 4 over 7 V2.
Excuse me, sir. Can you just go back to the circuit? I did not get down the resistor.
All right, so V1 is equal to 4 over 7. But remember, what we're interested in is the current flowing from the 1 volt source. So I include that. I now have the 4 over 7. Then based on our circuit, what is V2 equal to? What is V2 equal to?
1 volt.
1 volt. So we know that V1 is equal to 4 over 7. So what we need to find therefore are I1, 2, and 3 in terms of V1. V2, sorry. All right, so IY, all right, based on the circuit that we just looked at, IY would be equal to V2 minus V1 over 1K. That would be I1. V2 minus 2Vx over 2K. That would be I2. And V2 over 2K, that would be I3. So it gives us IY to be equal to 1 milliampere. So in a sense, we're saying that the 1 volt source when we connect it to that circuit, which has only a dependent source, it will produce 1 ampere. So it means, therefore, that this circuit has a Thevenin resistance of 1 kiloampere, 1 kilo ohm. All right, so our Thevenin is 1 kilo ohm. All right. So it's now 2:41. Let's just do this quickly. All right. So as you're seeing, we have both independent and a dependent source. We have independent, we have dependent. Yes. So it means that we have to find the short circuit and the short circuit current and the open circuit voltage. All right. So those are your equations. I'm just going to give you the values now. So E Thevenin is 20 and our short circuit is 3. All right. So I'm not doing it for you. I mean, I see some persons, just relaxing and looking at the screen. I'm not going to make their work easy. Right? Everybody needs to do the work so that we don't have the sort of hiccups we had in the test. And then with this, you can leave. There's one other statement there in the printed notes that I just like to highlight, and it speaks to maximum power transfer theorem. Now, with all that we have been doing, as you would have recognized, it really does not matter the magnitude or the magnitude of the resistor that you remove from the circuit. Doesn't matter, because what you're doing is to find the Thevenin equivalent at that point. So if you put a different resistor in the circuit and recalculate from scratch, find the current. If you simply put that resistor now connected to the Thevenin, you'll get the answer that you would have gotten working it from scratch. In other words, you can vary the load. It won't affect the answer when you look at the complete network. However, when it comes to maximum power transfer, the load resistance that will result in the maximum power being transferred to the load will be equal to the Thevenin or Norton resistance. What do I mean by that? Simply put, this is your Thevenin. What the theorem is saying, that is R Thevenin. This is E Thevenin. Maximum power transfer will occur when the load resistance is equal to the Thevenin resistance. All right? So that's the theory. That's all that is saying. You will explore that in greater detail in your labs. So I will not, spend any additional time going through it. But that's the theory. When you explore it, that will become clear. Here you have a question. We're asking you to find the. What are we asking you to find again? I have no idea. But just to see if what we have been doing is understood. You're gonna use, these are, this is a 4-mesh circuit. I want you to use Kirchhoff's laws. Kirchhoff's laws. And determine the current through the 12 ohm. So that's 1. So you're going to use Kirchhoff's. 2. You're going to use mesh. And find I2. Right? 3. You're going to use nodal. And find I2. And then 4thly, you're going to use Thevenin. And find I2. So those are the 4 methods I wanted to use in finding that current. Once you have done that, it's a matter of fact, I am going to make it a little more interesting. I will post it later, since everybody would have gone through this. I'll post it later as an assignment, all right, for submission. That said, all things being equal, when we meet next week, we will start the next topic, which will be AC circuits. Most of the notes are already in the printed notes, so it will be in your best interest to review it before you get here. In preparation for that class, if you are rusty with your complex numbers, it's a good time to review them, review complex numbers. Because we're going to be using a lot of that. All right. So complex numbers is going to form a major part of the course from here on. When we look at AC circuits, then we go over to resonance, and then we wrap up with complex waves. It's all going to be about complex numbers. All right. So once you have taken the circuit, you can leave the platform. That's it. Take care. Have a good afternoon.